So we were doing 2D moments. We got any questions on those? Are we okay with that stuff? The 2D stuff? All right. Why don't we go a little 3D here then, if we're good with that? All right, now sometimes we get into situations where we might have to deal with 3D moments, okay? So if you look at that weight that's being picked up and the way it's being torqued there, that would be kind of a 3D moment, all right? So let's have a look at these. Now a 3D moment, this is on 270, I think. There's three components of a 3D moment. There's a twist about a line running through a point and parallel to the x-axis, parallel to the y-axis, and parallel to the z-axis. So there's I, J, and K components of moment now. To determine your signs, use the right-hand rule. Twist your fingers of your right hand in the direction of the moment. Look at the direction your thumb points to get the sign. So the moment, whether an x moment is a moment about the x-axis. Same thing with the y and z moments. They're moments about the y and z axes. So you twist your fingers in the direction of the moment and then look at which way your thumb points on the axis, either positive or negative. Okay? So let's have a look at these. All right, so what kind of moments would both of these be, x, y, or z? Yeah, they're x. They're going to come around the x-axis. Now, actually, they also go around the y-axis, but I'm just showing the x part. Okay? So what's going to happen here is we're going to come up and around like that, correct? So if you twist your right fingers that direction, what do you got there? Positive or negative moment? That's going to be positive, yeah, okay? Now, what you're going to do is you're going to take the magnitude of the force times the perpendicular distance, so 300 times 4. So the moment, MAX is going to be 300 newtons times 4 meters, and it's going to be positive. That's going to be an I moment. So MAX, I guess in a vector sense there, would be 1,200 Newton meters. That would be I, that would be positive. Okay. So that would be the sign on that. How about the next one? What do we got for that? So get the sign and the magnitude of the next one. That's the next moment also. I've got it dimensioned there. Its distance from point A. So what do we got there? Maybe 1,800? Negative, yeah, okay. All right, now if you notice both of these, one thing on these 3D ones to keep in mind if you're looking at them is that you cover all three directions with the components in the moment. So what you have for both of those is a Y moment arm, a Z force, which gets you an X moment. So whenever you do these, you use each of those three letters once. Once for the force, once for the moment arm, once for the moment. So if you have, let's say, an X force and a Y moment arm, it'll be a Z moment, okay? So each letter is covered once for those three things: force, moment, arm, and moment. Okay. Okay, so that second one there is negative 1,800 Newton meters. So we okay with that? Doing all right? Yeah, remember that homework's due today, okay, that one problem. All right, so that's where you start with this stuff, okay? So that would be, if you express those as magnitudes, they just are as they are. If you want to put a unit vector on those to indicate direction, the unit vector would be I for both of them because they're about the x-axis. So the way I think about it is the moment is a wheel spinning. The moment vector is the axle of the wheel, normal to the plane of the moment, okay? So the moment vector is normal to the moment itself, okay? So the moment vector calls out the axis, the axle about which the wheel spins. Okay, if we want to find the moment of a force about a point, we find the x, y, and z components of the force, find the x, y, and z components of any position vector from the moment point to the force, and combine everything to create the moment. Now, I'm going to show you how to do these visually first, which is probably a challenging way to do it. Some of you will be quite challenged by this from my experience. You know, some people have a very good ability to visualize things. Some people struggle with that a little bit more, but don't worry if this doesn't come real naturally to you, because there's a mathematical operation called a cross product that we will use also to calculate these. So, but I want to start off with the fundamentals of this, so I want to do it visually first, although there is a more common method using what's called a cross product to do these. So let's say we've got this block that's attached with a rod at A. So we have a support at A. We're going to calculate moments about A. We've got that force that goes from corner B to corner C, 600 Newton force. We want to find the moment about A caused by that force. Okay, so our approach to doing this is going to be to use components, X, Y, and Z components, and combine them to get the moment components. That's how we're going to do this. What we want to do then is take this 600 Newton force and convert it into a force vector. Okay, and I do hope you know how to do this by now, because you know this is something we've been doing, and you do want to get competent with this and comfortable with it. So to find RBC, we take RC minus RB, we get negative 0.4, negative 0.7, 0.2. Take this square root of sum of the squares and get the magnitude. Divide through by the magnitude to get the unit vector. Factor the unit vector up by 600 because that's the magnitude of the force. You get the force vector. So those are the steps. That's how you do that, okay? We okay with that business there? All right. So once we've done that, we can put that force vector represented by its three components anywhere along its line of action we want. Okay, remember, you can do that when you do a moment. You can put the force anywhere on its line of action you care to put it. I think this first time through, I put it at C. So what I've done there, I've represented that 600 Newton force by its three components at C. So I can visualize that. And I think did I draw a sketch of that for you or no?
It's beside it.
Is it beside it? Okay, upper right there. And that's C, right? Okay, great, thanks. Okay, so there we go. Now what we want to do, we're going to do this visually first, is look at how those different points will affect point A. Or those different components of force, I should say, would affect point A. So let's see here. What's that 144 going to do? What kind of moment will that cause about point A? And there's different ways to do, there's two different ways I can think to visualize this, but which component would that be of moment, the 144?
Y.
That's not Y, or I can't hear what you said. Was it Y or I?
Y.
I said Y.
Yeah, it's Y. Yeah, it is. Okay. All right, what's going to happen here is it's going to come up and over like that. You all seeing that? Now, there's two ways I can think to visualize this. One way is to consider what I call a ball joint right there. You know what a ball joint is? It's like your hip is a ball joint. You got a ball and socket. You got one bone's a socket. The other's like a ball that fits in there, and that allows free rotation. You all know what I mean there? Okay. A trailer hitch is kind of a ball joint. Okay. We used to have these pen holders. They don't have them anymore, but You'd always tell if you were someone in important's office because they'd have this golden pen holder and they'd have their pen in their hands. Better act a certain way when you go to them offices, if you want to get good results. Okay, so here we go. So we got a ball joint there, and we got a little rod that sticks out to C, and if I do that and I push up on the rod, you see what that rod's going to do? It's going to come up and over, kind of rotating about the y-axis. Now, it's not actually the y-axis, it's a y line right there, right? Good? Now, the other way you can visualize it is with hinges and doors. So what you could do, you could put two hinges along this line from A in the y direction, two hinges like that, and you would open the door with, about those hinges with that 144 Newton force. You all know what I'm saying there? So if I pull on that door is going to come and rotate around those hinges. That's a y moment. That's two ways I can think to visualize that, okay? All right. How about the 506? What's that going to do?
Wouldn't that be absorbed by the rod?
Not the 506.
Because it's not in line with A. If it was in line, it would be. But it's going to rotate around the ends.
Not the 506? Okay, let me go back up just 1 minute here, and while you're looking at that, and point something out that kind of reinforces what I was saying earlier. With the 144, that's a Z force, right? And the moment arm is X, right? So what does that leave for the moment? Y, okay? Because X blank Z, we got X, Y, Z, those three things. So that's why that's a Y moment. Okay, now when you look at that 506, what's going on with that? I mean, if you can visualize it, or you can kind of put together this kind of, I don't know what you call it, a kind of a rule, three component rule. I don't know what you think. What kind of moment is it? Actually, it's positive.
It's going to spin on the z-axis.
We're looking at the 506. What kind of moment does the 506 cause about A?
Z is the Z moment.
Yeah, it's going on here, and it's hard for me to draw that, but it's going like that. It's going about the z-axis, right? Okay, and again, think of a ball joint at A extending out to C. Push on that horizontally. That's just going to wrap in the horizontal XY plane, rotating around the z-axis, or a line parallel to the z-axis through A, I guess I should say. All right. So that's going to be a Z moment. Okay. Now, similarly with the hinges, you could put a hinge here, put one there. The door, there's a door like that. Pull on it with the 506. That thing's going to wrap around about the Z, kind of a line parallel to the z-axis. You'll see in that, okay? And then the last little thing I can say is what the force goes in the Y. Actually, negative Y, but let's not worry about that right now. And then we've got an X moment arm, so that leaves Z for the moment. Okay. So however you do it, you can come up with that conclusion. Okay. Now this requires some visualization or something. Now again, if this isn't your thing, you have some difficulty with this, we'll find another way to calculate these. Don't worry about it. Okay. So what you do, you just multiply the forces and moment arms together because they are perpendicular to one another. Oh, how about the 289? I'm sorry. What does the 289 do?
Pulling directly away from A, so it's not happening.
Yeah, right. See, if here's A of my hand, and I'm pulling on this rod, I'm not making it rotate, I'm just pulling on it, okay? That's a force, it's not a moment. It's got a zero moment arm, because its line of action goes right through A. So it causes no moment about A. Okay, so the 289 does not cause a moment about A. So as far as moments go, you can ignore it, okay? You okay with that? Okay. So to find that moment vector, then we just multiply the numbers. The forces and moment arms are perpendicular, so we can multiply them together. And we got one for Y, so that's a J moment, and another one for Z, so that's a K moment. So there's the moment vector. So the moment vector represents all of these rotations, basically about lines parallel to different axes. Okay.
Oh, and because we moved all the forces up to point C,
Yeah.
they both have a distance of 1.
Yeah, they are, because they both have the same moment arm, right?
Okay, yeah.
The AC is the moment arm. Yeah, question?
Earlier when we were in physics, because we're kind of dealing with vectors in there too.
Yeah.
And everywhere else, you know?
Yeah, right. That's true. Yeah.
He's saying that Oregon State professors prefer us to write our notation with I, J, and K as opposed to vector brackets. Do you prefer that in here as well?
It's not an issue to me. Whatever way you like is fine. I noticed that the math, they use the brackets, right? In math?
Yeah.
And
Well, they use both.
they do. Okay, in engineering textbooks, they do use IJK, but I don't
Is
care.
that just a good habit for us to kind of start getting into though?
I don't know. I've been for years I've been telling people I don't care, do it however you want. I've never heard any feedback that caused anybody any problems, so I wouldn't worry about it. Okay. So just make it clear. I'm good. Okay. But I will say the engineering textbooks, they always have IJK from what I've seen. But I will also say that you're probably not going to do a whole lot of 3D vector mechanics down the road. You'll see it here. The most common major I can think of it in would be mechanicals, because you do a lot of space frames where you've got stuff going at all different angles all over the place. A lot of the civil stuff tends to be somewhat squared up, X and Y planes. You know. But I don't know, that's just, you know, that's my 10 cents on that for whatever it's worth. Okay, so there's the direction of those moments, okay? If that helps to visualize that, all right? Okay, so that's 3D moment visualization 101 right there, okay? So now we're ready to move into the graduate course, okay? So, but hang on, but let's get that moment vector, I'm sorry. So that moment vector, I plotted it up. I've just kind of, now that's always hard to do in 3D. It's always an approximation when you start drawing 3D on a flat piece of paper. But what I've done there is I've drawn a moment vector for A. I've gone in the J direction, 57.6. And who knows what that is. I don't have this scaled, but so I kind of went off in the J a little ways. Then I noticed in the Z direction, I'm going 3 or 4 times as much as I went in the Y, if you all know what I mean. So I proportioned up about 3 or 4 times what I had for the Y direction, and then I connected the ends, and that's roughly where that vector's at. Notice it has no X component. So there's my M sub A, okay? So that's now what that is, that's the axle about which the moment would spin. That's what that represents. So if this were a ball joint at A, and I had a rod out at C, and I pushed on it with this force, that thing would start to spin in a plane that's normal to the vector that I drew. That's the physical meaning of these things. Okay. All right with that? So there we go. Okay. Now let's go on to a more advanced case. Let's put that force instead of at C, which is the simplest place to put it. But just for fun, let's put it at B and analyze it that way. This is going to be a little more difficult to do, but let's just do it because I just want to get you an idea of what this stuff kind of means, so to speak, and how you can work with it. Now again, we're not going to actually do a lot of 3D moments visually. I just want you to see it this way because I just think it's so important to see things in your mind's eye when you're doing all these calculations. But let's get the moment of the force when it's placed at B about point A. Okay, so let's get some components going here. Let's get X and Y and Z. All right, let's start with that 144. What will that 144 do? What kind of moment will it cause about point A? I think that'll be an X, yeah, because that's going to come on up and over. Okay, and the magnitude of that will be what? Will be, and let's see about X. So I could think of a hinge line for that kind of here and here. Force pushes up on that top surface and rotates it about that x-axis. So what's the magnitude of that? Is it 144 newtons times what?
0.20.
0.7, I think,
Or no, yeah, 0.7.
because I want the line perpendicular to the force. Okay, are we good with that? How about, let's see. How about the 506? What's that going to do about A?
Spin it around Z. It'd be a Z moment, right?
Okay, I'm not seeing it about the Z because it's directly under A. So we're not getting a rotation.
Oh, okay.
You get it? Okay. But what does it do? What does it spin about?
It kind of looks like it's X, but in the opposite direction.
All right. So the opposite direction would be a negative then, wouldn't it?
Yeah.
Coming around that away. Okay, so that'll be a negative X. And what is that? 506 times, what's the moment arm on that?
0.2.
0.2. All right. You all okay with that? And if you rotate your fingers in the direction of that blue arrow, your thumb points into the page. That's clockwise, so that's negative. Okay. Okay, what else do we got going on here?
289.
Okay, the 289, now what's that going to do?
Gonna cause it to spin around Y line.
No, that's the Z moment.
Okay, I think that would be a Z moment. At least part of it would be. So what, if you're going to look at Z, what's the 289 multiplied by? What's the moment arm? 0.4. If we're doing a Z moment, what's the moment arm? See, the moment arm is the distance perpendicular to the force that connects it to a Z axis that goes through A.
It'd be 0.7.
0.7, okay. So what we're doing, we're hinging this line like that. So 289 times 0.7, positive or negative? Positive, okay, because that's running around that away. Come on now, pen. This thing. There we go. Something like that. Now, does that do anything else, though?
It also rotates it around the Y line.
Yeah, see, these forces, these components can cause more than one moment, and that's where this starts getting a little bit tricky. Just a little bit, so that's 289. And what's the moment arm on that?
0.2.
Yeah, I think it is. It's 0.2. Okay. So that's the last one here, I think. 289 newtons times 0.2 meters. See, that's hinging about this line right here. Okay? Is that positive or negative? It's positive because it goes under the line and back up the other side. So that's going like that. Positive Y. Okay? So there we go. So these get a little trickier. You know, I picked C first because it's the simplest one to see, but you know, if you get it at different locations, these can get trickier, okay? And I think I've got blanks there for you to be filling in if I remember right. So yeah, why don't we do that? Are we good with that? There we go. So something like that.
Good question.
Yeah.
So you're saying that if we applied those forces anywhere along that line, we'll end up with the same rotations? Okay. So they should be equal to each other. So
Yeah, that's one reason to do this is we're going to get the same answer. We're generating it in different ways, but we get to the same answer both times.
I think that's how you do like a self.
Yeah, and just to illustrate that concept too. Now look at what's happening there with the x component. Why did I write down 0 there? What's going on there? I multiplied the numbers. I got 100.8 minus 101.2. It's rounding area, and I knew it, so I just said it's 0. Okay. It's just rounding. Okay.
And you just kind of knew it was rounding error.
Because of the previous one, I knew there wasn't any x moment, so I knew that had to be rounding error, so I just zeroed it out. Okay. All right. Now, this is a little hard to do. I mean, you don't want to, obviously there's not a bunch of people analyzing this stuff and twirling their fingers around and trying to figure all this out. That's just not going to work real well. So as it turns out, there's a nice mathematical operation to do this with. It's called a cross product. Okay, so that's what we'll use to do this. But I wanted to show you the visual method because I think it's important to understand the difference between the mathematical model and what we're really dealing with as engineers. Those are different things. I've had some people tell me that a moment is a cross product, and that's not correct at all in my mind. What we just did are moments. That's what you want to visualize and see and understand, because especially when you start working, you're going to get in this environment. In school, everything's real calculation intensive, right? You got to calculate this and calculate that. But when you start working, the calculations aren't quite so much the issue. The issue is the assumptions and the understanding of what you're getting into. Oh yeah, I'm building this. This is going to have a moment on it. I better reinforce it somehow for that. You can analyze it. Once you figure out what it is, you'll have the tools to analyze about anything you need to. But the thing you're going to have to learn is to recognize what you got to analyze. That's really the point when you're working. It's a different world than school is. Okay. All right. So we okay with that? Everybody got that down? So why don't we have a look at this cross product stuff? Okay. We good? All right. Okay, so luckily some very smart mathematicians came up with this. And again, I doubt they were thinking of moments when they did this. I don't know, mathematicians just play around with numbers and come up with stuff. I'm not quite sure why, but they do. And then engineers and scientists go, oh, yeah, that's a great way to model such, and off they go. Usually the mathematicians are out in front doing the theory, and then the people that use it see those models and use them. I mean, there's even a thing, Einstein even accredited some mathematician who invented some math like 2 years before Einstein came up with relativity. And he wrote down, thanks to so-and-so for coming up with this stuff, because I used it to figure this out. It's pretty good. So usually it takes a little longer before the math's invented to really find uses for it. Okay, so what we're going to use here is a cross product. Okay, cross product is C is A crossed with B. So that's not a multiplication symbol. That's a vector operation. It's called a cross. All right. Now this is, and what we do here, the magnitude of C is AB sine theta now. Before on the dot, it was AB cosine theta. For a cross, it's AB sine theta. Now C is a vector normal to the plane formed by A and B. And the right-hand rule determines the direction of C. So if you take your fingers, point them towards A, rotate them towards B with your right hand, your thumb will point in the direction of C. So the cross product is a vector, unlike the dot product, which is not. Cross product is. Okay, so I got a little bit of a sketch there, kind of a 3D sketch. What I'm trying to get at there is a flat disk with a vector normal to it. The disk is the plane that contains A and B. The angle between them is theta there. And then C is normal to the plane. I don't know, should I try putting a perpendicular symbol in there, something like that? That's what I'm trying to convey there in that flat piece of paper, okay? All right. Now let's do the same sort of deal we did with the dot product to figure out how to calculate a cross product. Now, if you're in Math 254, you're probably doing this, or you've done it, or you're about to do it, or something. I'm not quite sure where you're at with it. We'll do it in here. You probably do it in physics too. You'll see this a few different times. Now, one thing I do want to point out to you on these vector operations, I give both of them to you, okay? The lower left-hand corner of your formula sheet, there is the formula for a dot product and then a cross product. So the formula for this thing is right here if you need it, okay? It's there. Okay, so don't worry about that. You've got these things right on the formula sheet, lower left-hand corner. Well, let's go ahead and derive this, though. Okay, so the definition is AB sine theta. Let's look at what happens with the unit vectors. If you dot two like unit vectors together, the angle between them is 0, and the sine of 0 is 0. So when you dot two like unit vectors together, they zero out. when we dot unlike unit vectors together, what we get is the third unit vector, because the cross product is normal to the plane of the two vectors you cross. So for instance, if you cross I and j, you'll get k for the cross product. The magnitude of I is 1, the magnitude of j is 1. 1 times 1 is 1, and the direction is normal to the plane containing I and j. Well, that's the k direction, okay? By the right-hand rule, that'll be a positive k. Okay? So when you cross unlike unit vectors together, you get the third unit vector as your result, either positive or negative, depending on how the right-hand rule points. So I've got all the crosses for all the vectors here shown in kind of a matrix form right there. Okay? So that's what happens when you cross unit vectors together. And you could use your right hand and prove all those out, but I think we'll take it as, we'll just go with that, okay? So if you cross two vectors together, A and B, so you got AX, I, AYJ, AZK, and BXI, BYJ, BZK, and cross them, we just cross all the components together, okay? So we get a big 3 by 3 kind of matrix thing going there. AX, BX, I dot I, that zeroes out. AX, BY, I dot J, which is K. AX, BZ, I was saying dot, wasn't I? That was wrong. So AX, BX, I crossed with I, which is 0. AX, BY, I crossed with J, which is K. AX, BZ, I crossed with K, which is a negative J, etc., etc. And then I just collect the terms right there. There's the formula that's in your formula sheet. You can also do this with a determinant, which is, if I remember right, it's how I learned it. And you'll get to the same result. There's also a little trick where you can put two columns to the right of the determinant and do kind of all right down crosses and all left down crosses. However the heck you do it, I don't care. Okay, just get it, okay? Now, again, if you don't know how to do it, it's right on the formula sheet. So it's just there, the formula, okay? So be aware of that. So when we cross vector A and vector B together, we get that. That's the bottom line right there. Okay? All right, we good? All right, now let's use this thing because this is a tool that we can use to calculate a moment. Okay, but let's first just do an example here. I think I've got a little computer generated thing. Yeah, there we go. So let's find A crossed with B. If A is 3I minus 4J plus 6K and B is minus 5I plus 2J plus 7K. Okay. So again, you'll have the formula laid out like that on your formula sheet if you need to do this. All you do is just combine the numbers the right way. So the way I learned to do this by a very scary math professor, so I still do it this way because I don't ever want to make him angry. I just don't want to do that. So what I do is if I want the I component, I cross off the top row and the top and the left, the I column, and I cross what's left. So I'll get minus 4 times 7 minus, remember that negative because it's minus 6 times 2, and that'll be the I component. Now, if I was smart, I'd just use this formula because I've got it and it's right there, but I just don't want to get him angry. I really don't want to do that. So I just do it this way. Okay. All right. All right. Then we've got the J column, top row, cross what's left. Now, the important thing on this is there's a negative in there for the J component. You got to remember that. And then you cross what's left, you're going to get 3 times 7 minus 6 times a negative 5. Okay, so you got to remember that negative in there. And then for the last one, what you do is you cross out the top row and cross out the K column and cross what's left. So 3 times 2 minus negative 4 times negative 5. And that's just how I do it. But again, whatever way works for you is fine with me. Watch your signs when you're doing this. It's the first one minus the second one inside the parentheses, plus you got to remember that negative in front of the j component. All right, collect terms, and there's A crossed with B right there. It's negative 40I minus 51J minus 14K. Okay? So that's how that goes. All right, now let's have a look at getting a moment out of this, okay? That's what we want to do with it. That's our purpose for this tool in engineering here, is to get moments. So what we do is we take, to get the moment about A, we take a position vector from A to the force, any position vector you want, that's R, and you cross it with the force vector. So what I've done, I've substituted in R for the vector A and F for the vector B, and written it out, the cross out, as R crossed with F. So if you just do a cross product between a position vector from A to any point on the force, and you cross it with the force vector, what you will get that comes out is the 3D moment vector. That will just come out magically. It'll just pop right out. Okay? So that's the bottom line right there, is that formula, and on your formula sheet, that formula. This will allow you to automatically calculate 3D moment vectors. Okay? Now I'm sure you're wondering why. Why does this work? That's a good question. I'll answer that for you. Okay, so what we got here, we've got the point A. We're going to draw a vector that connects it to the force. Now, I can't visualize that well in 3D, so I break it down into 2D sometimes if I want to figure it out, okay? That helps me sometimes. So what I'm doing here, I'm taking point A, I'm drawing a vector from A to the force, call that R, any vector I want from A to the force, and I cross R with F. What I get out of that is a vector that's normal to the plane, and we were talking about that already, how the moment's a wheel for the plane. The moment vector is the axle of the wheel, normal to the plane. And we went over that earlier. That works just fine. And then the magnitude is RF sine of theta. That's the magnitude of a cross product. So if I look at the RF sine theta stuff in 2D, let's have a look. And here's a sketch that'll show us that. I've got point A, and I've got the position vector R that goes from A to the force. Okay. Now to get the 2D moment, what I would take would be the force magnitude times the distance that's perpendicular to the force to A, which would be D. But notice that my definition for a cross product is any vector that goes from A to F. All right. So what we would look at would be that angle between the R vector and the F vector, which would be theta. That would be this angle right there, and look what I've got. I've got a nice little right triangle there, don't I? Okay, I've got the perpendicular distance over here. I've got the force right there. I've got R right here, and I've got this angle theta. So if I take the magnitude of R, which would be the hypotenuse of that triangle, multiply it by sine theta, that will get me automatically that perpendicular distance. Okay. So what I've got there for the magnitude of the cross product of R crossed F is RF times the sine of theta. R sine theta is D, that perpendicular distance, and then I've still got that F in there. So a cross product gets me F times D, D being the perpendicular distance. It just pops right out. And in addition to that, I've got the vector normal to the plane. That's how it ought to be. So that's why that cross product generates a 3D moment for me. It's got the proper direction, it's got the proper magnitude. Okay? So we don't have to do all this visualization and stuff with our right hand. All we got to do is find an R vector, cross it with the F vector, and out comes the moment. That's definitely how I would suggest doing these 3D moments, when you actually calculate them. Okay? We okay with that? I don't think we got enough time to do an example. We'll probably do that tomorrow, okay? But that's the tool that we'll use to calculate 3D moments. All right? So we'll call it good here.